the YouTube too, because your talk is live cast for how do I say? It's broadcasted in the YouTube too. So
Sure. Okay.
let me slowly start. So Professor Roman Vasseur, am I pronouncing it right or? Okay.
Well, sir, yeah.
So
Better than many of my American friends.
yeah. So Professor Vasseur got his PhD in Paris under famous people who are working on the CFTs. So for example, Professor Hubert Salor is, I guess, very one of the most expert in the CFTs. So during this PhD times, I guess he worked on the CFTs, and after that, he moved to the Berkeley for his postdoc under Joel Moore, where I met him. And he did a lot of important work about the random systems and the driving forecast systems and the non-equilibrium dynamics. So he's a real expert, one of the real expert who are working on the randoms and the dynamical systems. And he got the professorship at the University of the Massachusetts. And I guess today he's going to present his work on the entanglement transitions. So you can start, Roma. Yeah.
Thanks. Yeah, thanks a lot for the invitation. And yeah, I mean, it's great to be here. Like I said, I almost feel jet lagged given the time slot. But yeah, I hope I can visit in person soon once things go back to normal, whenever that is. But yeah, in the meantime, so today I want to tell you about some kind of general line of research I've been pursuing for many years now, which has to do with what I call entanglement transitions. So part of this talk will be to kind of to explain what I mean by entanglement transitions. So in a nutshell, there will be phase transitions that occur in quantum systems where the key quantity that is changing, so if you want some kind of order parameter, will be quantum entanglement. Okay, and when I say change, I will mean really a dramatic change. So if you're familiar with quantum entanglement, you could think maybe topological phase transitions would be phases, for example, where patterns of quantum entanglement are changing, but here I will mean something kind of more dramatic that will only occur in dynamical settings. Okay, so it will have to do with non-equilibrium dynamics in general. Okay. So a large part of this talk will be explaining what I mean, motivate those entanglement transitions, and review recent examples which have to do with the so-called measurement-induced entanglement transitions, which have attracted quite a bit of attention recently. Okay. Right, so before I get started, let me thank my collaborators on this. So this is in particular some line of research I've started with the first three people here: Andrew Potter, who's at UT Austin, Yizhuang Yu, who's in our faculty at UC San Diego, and Andreas Ludwig in Santa Barbara. The photo is not exactly up to date, and more recently, I've collaborated also with Xiaoming Chen, who's at Station Q and moving to Cornell. And even more recently, I'm going to mention some results with my student, Javier Lopez, and Braden Ware, who's a postdoc with me at UMass. Okay. All right, so let me get started, and please feel free to interrupt me with questions. So first of all, I want to kind of motivate this talk and this work in kind of broader context of kind of general questions to motivate why those entanglement transitions could be interesting. So one of the questions I've been thinking about for many years, starting pretty much at Berkeley, was to think of universality at infinite aperture, and I will explain what I mean in a minute. So if you hear about this, this sentence sounds like it's maybe nonsensical. Usually in physics, where we think of universality, we have in mind, the field of statistical physics and all those beautiful unifying concepts that we learn in, statistical physics in undergrad or grad school. about the whole normalization group, scaling laws, universality, phase transitions, and all those things we all like as condensed matter people, or in general theoretical physicists or experimental physicists for that matter. And we also learned that interesting universal phenomena happen at low energy and low temperature, right? And we like universality because it means that we can have properties that don't depend on some microscopic details or chemical makeup, and we can have nice maybe toy models that we can use to understand the physics at play here. Okay. So of course, if we have a typical condensed matter or phase transition book, we also have like phase diagrams like this in mind. Usually, this would be an equilibrium phase diagram. Say I have temperature, and I have a tuning parameter G that I call G, and I imagine that maybe this tuning parameter is driving a phase transition, a quantum phase transition at 0 temperature between an ordered state, so I don't know, an antiferromagnet or ferromagnet, and maybe a disordered state here. And there's a quantum critical point at 0 temperature, and at finite temperature you can have a classical phase transition. You can have a quantum critical regime. But the general scenario that is that if you go to very high temperature, in this kind of high energy regime here, you won't get really any interesting phase transitions. That regime will be not only it will be largely non-universal. That is, it will be dependent on macroscopic details, and there's not going to be second phase transitions or anything fascinating like this going on. And it's also a very classical regime, you would think, because it's at very high temperature. Okay. So nevertheless, in some way, the systems I'm going to be talking about, I think of them as in this high energy regime, not exactly in this setup, and they will be intrinsically quantum, and you will have some phase transitions that you can think will have universality. Okay. So the caveat, though, is of course I'm not exactly going to be in this setup. I'm not going to be in thermal equilibrium, but nevertheless, I'm still going to be in some kind of high energy regime here. Okay. So one of my main motivations of this talk is to think about dynamics. That is my main, field in general. That's most of what I think about has to do with the dynamics of many-body quantum systems. Here I put isolated quantum systems. Actually, today I'm going to be talking about open quantum systems. But let me start with isolated for a bit. So the motivation is to think about, again, isolated quantum systems, many-body quantum systems that are well isolated from the environment. This is largely motivated by many different, wonderful experimental platforms, including some example I've listed here. And the type of physical setup that we have in mind is very different in many of those systems. Instead of thinking of your system as being connected to a bath, it has some temperature and it's in equilibrium. The type of setup we have in mind is to start from a given quantum state. Say you could have spins, and you could start from some initial state, which is a product state of those spins. And then you want to think of time evolution just given by the Schrödinger equation. Okay, and you could think about either the dynamics of the system or maybe the state of the system at long times. Okay. So typically, say you could think of, again, spins or fermions on the lattice with bounded spectrum. Typically you could think the initial state that you consider could be like a highly excited state. So something that's very far away from the ground state will kind of overlap all eigenstates of the system, of the true system. This is a cartoon of what, the many-body spectrum of your system could look like. And so morally, you could think that this initial state could have a very high effective temperature, could be at effectively infinite temperature. And yet there are systems in which the dynamics is going to be kind of very non-trivial. Okay. So in particular, in this talk, the title of my talk is Entanglement Transitions. So I'm going to be focusing on quantum entanglement, okay, and in particular entanglement entropies. So let me just remind you a few basic things about entanglement entropy that you may be familiar with, but I just want to make sure that we're all on the same page. So I'm going to be focusing on pretty much this setup of dynamics of state. You start from a state, say a product state, which has 0 entanglement between all your spins, if you have spins, okay? And I'm going to think of kind of generic time evolution under some interacting Hamiltonian that, again, is interacting and has local interactions, okay? So okay, in general, like for now, I'm talking about the unitary evolution. Okay, so closed quantum system. So of course, this evolution is unitary, but we know, and you know, many people have been working on this for quite some time now, that we expect that many body quantum systems generically, and there are exceptions, will thermalize. And that is to say that if you think of the behavior of local observables at long times, they won't remember about your full initial state, okay? Even though technically it's unitary evolution, so the memory of the initial state is still there in the quantum system, you're not losing information. But if you focus on like local quantities, you will effectively forget entirely about the initial state, and the only thing you will remember are conserved quantities like energy or particle number. So in other words, you will kind of reach local equilibrium. And so what it means is, you know, one way to pictorially think of it is that if you take a subsystem, I call it A of a system, it will, you can think that the rest of the system is effectively acting as a bath for that subsystem. Okay, and so the memory of the initial state is kind of scrambled by the dynamics into highly non-local degrees of freedom that you cannot measure with physical local observables. Okay, so that's thermalization in 1 minute. And so the, you know, more in equation, what it means is that if you take the reduced density matrix of your system, so even though the full system is in a pure state, you can take a reduced density matrix focusing on the subsystem A. At long times, we expect that generically it will approach a mixed state, which will be, say, if you have only energy as a conserved quantity, will look like a Gibbs ensemble with some effective temperature. Okay, and that temperature will be set by the initial states, by the energy density of the initial state you started with. Okay, so all right. So what it means in practice for me for this talk is that, okay, so this is a, you know, reduced density matrix. It's, you can compute its entropy. It's von Neumann entropy, right? Just by trace rho log rho. This entropy at long times here will coincide with the microcanonical entropy. What it means is that it will also be extensive. And so in the context of entanglement, this is known as volume law entanglement behavior. Okay. So what it means, again, and translating into entanglement, is that your system has become highly entangled with the rest of the system A bar, okay, and has very high entanglement. So that's at long times, and so this will scale with the volume. Okay, so this is this volume law scaling of entanglement at long times, and as a function of time, entanglement grows linearly, and this is something that has been studied by many people, and, you know, in the context of CFTs first in particular, but more recently in many different contexts of non-integrable systems. Okay, so entanglement grows fairly fast, fairly rapidly as a function of time, and then it saturates to something that scales with system size. Well, okay, so that's kind of the generic behavior we have in thermalizing systems. And so it is in some way universal, but it's also kind of, you know, generic. Okay. So actually in this talk, so I had, again, I'm going to talk about entanglement transitions. So I'm going to be interested in cases where we can, again, tune a parameter and have a transition in how this entanglement is changing or scaling in some way. Okay. So the first question you could ask is, okay, is it possible to, is it really that generic of a scenario? Do we always get entanglement growing that fast and growing to a volume law? And so the answer is no, and there's one well-known example, which is close to my heart, but which I'm not going to talk about too much today, which is localization, or many-body localization in particular. So if you take, say, a 1D system, so here I'm working with fermions, but you imagine that you have some interactions, but you also have strong random chemical potentials or fields if you have spins. It's now, you know, there's been many works on this. Despite the interactions, it's believed you can have a many-body localized regime if disorder is strong enough, where basically the scenario outlined here doesn't apply. The system will not thermalize. It will not reach equilibrium on its own. The subsystems will not reach thermal equilibrium, and entanglement will grow much more slowly than linearly. It will grow as a log. Okay. It actually still approaches a volume law at long times that I won't really talk about, but it grows very slowly. And if you consider the many-body eigenstate of such a Hamiltonian, they will have area law scaling of entanglement. Okay. Meaning the entanglement would only scale with the boundaries of the interval you take. So in 1D, it will be a constant. Okay. Whereas if you did the same for a thermal system, it's believed by the so-called eigenstate thermalization hypothesis that and it's widely checked numerically and in many other ways that the entanglement in each eigenstate is volume law. Okay. So this is one case where you have a completely different scaling of entanglement. Here it's due to disorder. All right, so let me come to kind of the main punchline of what I mean by entanglement transitions. So I'm going to be talking about those entanglement transitions. Those entanglement will either be dynamical. Those transitions will either be dynamical, that is, they will occur in dynamics, or you can think of them as eigenstate transitions in some cases, like in the many-body localization case, and meaning if you measure entanglement in an eigenstate, highly excited eigenstate of the system, it will change as a function of some parameter. Okay. And so the basic question, the basic type of setup I'm going to talk about is, imagine we have a parameter, again, I call it G here, for which we're going to change the behavior of entanglement as it grows with time, and also as it saturates with system size, or as it behaves in eigenstates. And so the two different behaviors I'm going to talk about is, again, the first one is similar to those thermalizing systems. I'm mostly going to be talking about 1D systems here. So this is why I only have a LA here. So it saturates with something scaling with the size of the interval you take. So it grows linearly and it saturates to something that scales with LA. Okay. And as you crank up this parameter G, you could have a phase transition, which again, I'm going to call an entanglement transition, where here we'll just saturate to a value, for example, that doesn't depend with system size. Okay, or say in the case of many-body localization, I just mentioned it would grow logarithmically. But in any case, something dramatic happens which has to do with entanglement dynamics. For all the transitions I'm going to talk about, I'm actually going to give you 3 examples that at least I know of, and I'm pretty sure there are others. Where there's different scenarios, but in all of them, I think everyone agrees that really entanglement is the key quantity to think about here in all those transitions. Okay.
So I have a brief question. So
yeah, please go ahead.
In the introductions, you said it, universalities. So do they have some universalities too here?
Yeah. So that will be absolutely. So that will be one of the main punchline. I think is like all the transitions I'm going to talk about. I believe they have universal critical exponents, and that won't depend on many microscopic details. Okay. Despite the fact that they occur again. So they have to do with entanglement, quantum mechanics, and they occur in this kind of high energy regime in some way. There's no low temperature in any case here. But there will be some universality.
I see. And then they have they are always continuous transitions. Is it something you are going?
The one I'm going to talk about, yes, that's correct. They will all be second order phase transition. Well, okay, yes.
But there are also first order transitions too.
Yeah, well, not in the cases. I don't know of an entanglement transition that's.
That was my question.
Like the first example I'm going to talk about, which is the ambient transition, has some discontinuous aspects, but it's definitely not first order.
I see. Yeah.
Okay. So, but they are like universal. There are universal critical exponents, I think, for everything I'm going to talk about.
I see. Okay, I will wait more. Yeah, thanks.
Sure. No, but that's a very good question, and that's pretty much going to be the punchline. I think that's you have such universality in those entanglement transitions, even though they're very much not in the regime where you usually expect universality.
Good. Yeah. Cool. Thanks.
Is there any other question before I go ahead? Okay. All right. So if not, let me just keep going and just mention a few examples. So the first one I already mentioned, and I'm not going to spend too much time on it. This is the so-called many-body localization transition. Okay. And just very briefly, in a nutshell, I think that was actually the first example of an entanglement transition that at least I know about. And really, it has to do with just, again, think of an isolated quantum system in 1D. Okay, so you could be spins or it could be fermions with bounded on-site Hilbert space. You think about the dynamics, and the claim is there are two regimes, two phases, really dynamical phases. Either the system will thermalize, you'll forget about initial conditions, you'll get, everything will be fine in statistical mechanics and so on. But in terms of entanglement, you'll have volume law entanglements, in eigenstates, and as a function of time, entanglement will grow rapidly. But if you crank up disorder enough, you'll have this many-body localized regime where, okay, there are many things interesting about this regime that I'm not going to talk about, but in particular that the eigenstates, for example, of the system will have area law entanglement. So if you want, really entanglement is like an order parameter in some vague sense. Okay, it's not like a local order parameter, but it is some quantity which is jumping. If you take S divided by the system size, this is going to have a jump at the transition. Okay. So that's one example, a clear example of what we'll call an entanglement transition. And I think among many people working on many-body localization, everyone kind of agrees that entanglement is really the right language to think about that transition, despite the fact that there are many other observables, more direct things that you can measure, in real life. But thinking conceptually about entanglement is extremely useful for this transition. Okay, and in fact, most of our understanding of that transition has to do with entanglement. At least I would argue. Okay, so again, I promised I would not talk too much about the many-body localization transition. So let me give you another example. And this one I'm going to spend a lot more time on. So this is the transition which is now known as the measurement-induced entanglement transition. And it was introduced in those two beautiful papers by Skinner, Ruman, and Nahum, Lee, Chen, and Fisher, two papers that appeared pretty much at the same time. They started talking about this a couple of years ago now. Okay. All right. So what is it about? So it's slightly different, but it still has to do with dynamics, and there's still a transition in entanglement as a function of time or as a function of system size if you wait long enough. Okay. So let me tell you a little bit about just the specific models, and then I'll mention how general this is. Okay. So this transition is pretty simple in some way. So you're thinking of a system, it works in higher dimensions, but again, I'm going to do 1D, a 1D quantum system. Again, let's imagine we have just spins or qubits, or it could be any D-level system, and they live in 1D and they have local interactions. And we're going to think of modeling the dynamics in some very generic way. And in particular, so this is actually not needed. It's going to be useful just for the theory, but it's not needed to have the transition I'm going to talk about. And so this is where the universality is going to come in. Okay, so the toy model, if you want, the Ising model of this transition is think of some chaotic dynamics or some thermalizing dynamics, in which everything we're going to keep is only to have unitarity of quantum mechanics, and to have local interactions and nothing else. Okay, no conserved quantity, not even energy. And so one way to do this, which has become extremely popular over the years, to work with a random unitary circuit. Okay, so this is depicted here. So each line, so this is time, this is position. We have a bunch of, again, spins. Let's spin 1/2. Okay. Each box is a unitary gate, okay, so meaning it's just a unitary matrix acting on the spins, and that is generically going to entangle your spins. And they have this kind of brick wall pattern, okay. Each here unitary is drawn as random, okay. So it's a random unitary also in time and in space, okay. So there are different models. It could repeat in time, in which case it would be a periodically driven system, like a Floquet system. Here, we're taking everything random, position, and time. Okay, so there's no conserved quantity whatsoever. And so such models have been studied without the measurements I'm going to talk about, and they have entanglement that grows linearly, and they're kind of good models for just generic entanglement behavior. Okay. Again, it's just important for the model, but like the transition I'm going to talk about also works for Hamiltonian systems and so on. So it's not like a, okay. So this is, so far we just have random unitary dynamics, and this just, it's a typical model of kind of maximally chaotic dynamics in some way, and it's just going to give you random, fast entanglement growth. Okay. So
can I ask another question? Sorry.
Sure, please go ahead.
So you said it's randoms, but there could be some correlations between the unitaries if I wish. So like a disorder, so it could be completely random, or there could be some correlation.
So here, like every gate is independently drawn. There are no correlations. I mean, in principle, again, it's not going to be crucial for the. I'm going to mention how general the transition is afterwards. But so far, this is just a model for the chaotic dynamics. In principle, you could take any unitary evolution, which is thermalizing. But here, the model, every gate is taken from, you take a Haar measure on your unitary group, and you just pick a random matrix every time if you wanted to do this numerically.
I see. So even if I impose certain correlation between the unitaries, that doesn't affect much about the.
So that's the thing, yeah. So I will. Okay, so let me mention what the transition is. But if you even take a Hamiltonian system,
right,
all your gates will be the same and so on, and then it will still have that transition. Okay.
Oh, okay.
So for some people that do like numerics, you can think of it as, when you do TBD or something like this, and you trotterize your system. This is kind of the same quantum circuit that you get. Here we're just making all the gates random as a model, and it will help the theory a lot. But again, the transition I'm going to talk about does exist in general.
Okay.
And people have actually checked it exists if you did like a normal time evolution. Okay.
Yeah.
Okay, so this is scrambling or chaotic dynamics, that leads to fast entanglement growth. And so the other ingredient is going to be to have measurements. Okay. So measurements in the quantum mechanics sense, meaning that they are projective. And so what it means is that locally, so every time I have a black dot here, with probability P, okay, P will be a parameter, you will measure that spin, say in the Z basis. If you have just a qubit, I'm just going to measure, whether it's up or down. And it's a projective measurement, meaning that after the measurement, my spin will be projected to that state, okay? And the outcomes will occur with the usual rules of quantum mechanics, with weight probability, that will depend on the wave function itself, okay? So it's pretty clear. So we're going to think of the measurements in the so-called quantum trajectory language. That is to say, I'm always going to imagine I have a pure state. So I have a wave function. It's a pure state, a time evolved with that unitary evolution. Every time you measure it, I flip a coin, I have this probability P, and then I have a measurement outcome. And at the end of the day, I get a wave function, which is projected, which is still a nice pure state. Okay. So I always have a nice wave function. And that's actually going to be important for the transition. Okay. So every time, different measurement outcomes will give you different wave functions, and those will be different quantum trajectories, okay, in the space of the outcome of measurement. Okay. So it's pretty clear that if you measure all the time, say if you have P equals 1, you will actually kill any entanglement. So that is to say, let's say you measure every single spin. Let's say you measure spin 1, it was up, you measure spin 2, it was up, measure spin down, spin 3, it was down, and so on. So you keep doing this. At the end of the day, you're just projected back to a product state, which has 0 entanglement. Okay, so it's clear if you P is 1, so if you measure everybody, you're just by definition projecting onto a product state. So you kill any entanglement. So what those people realize is that as a function of this parameter P, you can actually have a transition. And so you can think you have a competition between scrambling or chaotic dynamics and the measurements, which in some way are disentangling. Okay, once you measure and you have this projection operation, you disentangle your system in some way. And so you can see this either as a function of time. Here, what's plotted, so this is numerics. So that was done by using Clifford gates, but that's a technical detail. So this is showing entanglement of half of the system as a function of the size of the interval. So this is done in the so-called steady state. So you wait a very long time, you do many of the measurements. And you look at things as a function of this subsystem size. So you see that if P is 0, it grows in, okay, it's a log-log scale, but this is volume law, so it scales with L here. But if you crank up P, and here P is not that big, it's just 0.3, you see it just saturates to basically just a constant, which doesn't scale at all. Okay, and it's just perfectly saturated with the subsystem. And in the middle, I think where they say it's where you have the black curve, you have a transition. Okay, and I'll show some scaling with this. Okay. So this is basically, okay, this is in a nutshell, this measurement-induced transition. It was first introduced again using circuits, but it's kind of a lot more general than this. And you can think that in general, it's going to be the difference between just chaotic dynamics of just any system you would want that has thermalizing dynamics and measuring locally with some, with some rates. So this is just to say, like, in some way, like this transition became almost a subfield in itself, which is slightly exaggerating. So this is just a workshop we had like a couple of weeks ago, actually, in Dresden. So it was a virtual workshop that I co-organized, and that was pretty much on related topics. And you see the figure here is pretty much on those circuits. So this is just to say it has, it's a pretty big field, including many people from quantum information. And so there are many, there's been, since those papers, there's been actually many results and variants of that transition. So this is just mentioning some of the results. So what I'm going to talk about today in the rest of the time I have is like, I'm going to spend some time explaining a little bit more how we understand that transition, why we think it's universal and has universal properties. There's been numerics, so talking about more realistic models, there's been numerics, for example, on the Bose-Hubbard model, okay, where they truncated the number of bosons per site, but like some more generic Hamiltonian dynamics where you still find a transition, okay, you do measurements still, so you really don't need those random gates. This is just for the theory. If you don't like entanglement, so this is not for this, well, you shouldn't be attending this talk, I guess, and but it's, so you can think of different observables, and there are many variants again, and even recently people thought about transition that would occur if you have only measurements. Okay. So before I move on, let me just mention very briefly a third example, which is actually a bit earlier, which has to do with tensor networks. Okay, so it's the last example I'm going to talk about of an entanglement transitions. So it's a bit more formal, so I'm not going to spend too much time on it. So it's a bit less appealing maybe than the measurement transition. So it has to do with thinking of tensor networks. Okay, so tensor networks are like quantities that are that nice to draw. So each node here you should think as a tensor. Each leg corresponds to indices of the tensor, and every time you have a connected leg, it means you sum over the elements of the tensor. Okay, so it's like a contraction between the tensors. Each index is a degree of freedom that ranges from 1 to an integer we call bond dimension. Okay, and so here you see I have many tensors which are all connected, and so every time this would be hard to compute numerically, you have to sum over all. Every time you have a line, you have to contract the tensors. And at the boundary of this graph here, you see I have dangling legs. Okay, and those we would think are like degrees of freedom or some wave function. Okay, and so this could be representing a one-dimensional, say, wave function. Okay, so okay, if you're familiar with DMRG or things like this, or matrix product states, okay, so you probably know all this tensor network jargon. So here I'm thinking of tensor networks a bit more generally. I'm imagining it would have any type of graph, that's maybe not appropriate for numerics, but as a way of generating wave functions. And similarly to this random unitary model here, actually, in that paper, we were thinking about wave functions like this that were given with each node was a random tensor. Okay, so we were kind of thinking of ensembles, if you want, of wave functions. And the claim is, again, you have transitions here as a function of this parameter, the so-called bond dimension, which in principle is an integer, but you can easily make it a real number with technicalities I won't talk about. So you can think of tuning that parameter, the number of degrees of freedom in your tensor, and you can also get transitions as a function of that parameter. If that bond dimension is large, you can get volume law scaling if you think of your 1D system, but if the bond dimension is small, you can have area law scaling. And it doesn't look like it, but actually this transition in tensor networks is extremely closely related to this measurement problem I was telling you about. So again, this is partly that universality that comes back in, and hopefully that will become a bit clearer in the next few slides. But those problems are actually almost the same. They have some tiny differences, but even though they look absolutely completely different, as the second one, this third problem here looks almost like a mathematical problem, where you give yourself random ensembles of wave function and you ask about their properties. But yeah, this ends up being very closely related to this measurement transition. Okay. So those are all the examples I'm going to talk about. And so in the time I have left in this talk, I'm just going to focus on one, which is this measurement transition. And I'm going to try to tell you more about it. And again, we'll we'll have just some critical exponents and universality and just explain, just seeing some at least concrete examples of this in for this specific transition. Okay. Okay, so on this slide, what I'm showing you are just some numerical results from like one of the early papers on this of this measurement transition. So what did people compute? So they computed entanglement entropies. So they formed the reduced density matrix and they computed entropies. So you can compute von Neumann entropies or you can compute Rényi entropies that are defined in this way, and they all behave pretty much in the same way. Okay, and so as a function of, so this is again in this, if you wait long enough and you plot things versus system size, and you see the first plot looks a lot like a typical type of collapse you would see in a Monte Carlo or quantum Monte Carlo paper. Okay, so it's a very nice finite size collapse showing really a phase transition, and they extracted critical exponents. In particular, there's a dynamical exponent that numerically was observed to be very close to 1, and I will actually argue it's exactly 1. So the dynamical exponent relates position and time here. And it's not obvious at all that in that problem, there should be any type of symmetry between position and time, right? So there's a real time dynamic that's unitary where you make the measurement and then you have space. But it turns out there is a dynamical exponent 1, and there's a correlation length exponent which is close to 1.3. Okay. And again, those exponents, people have tried various families of even gates and different setups, and they don't depend on microscopic details. Okay. Even more than this, like it was observed relatively early that there's actually some conformal invariance in this problem. So it's not even that the dynamical exponent is 1. There's a full like blown conformal invariance as you would have in a 2D StatMech model, and I'm going to actually explain this. And so one way this was observed is by computing the so-called mutual information of okay, so you have 2 intervals A and B, and you compute this quantity, the entanglement entropy of A plus the entanglement entropy of B minus the entanglement entropy of A union B. Okay. In principle, it depends. So again, you take a periodic system. In principle, it depends on x1, x2, x3, x4. So it depends on those 4 positions. And what people found numerically is they depend only on this parameter eta, which is known as a cross ratio. So only a particular combination of those parameters, and you can see all the data collapses here. And so, okay, for people familiar with conformal invariance, this is an extremely strong test of some conformal invariance. But so I will actually explain this in a couple of slides. Okay. So there's a lot going on in that transition, and again, it seems to behave as a normal phase transition, even though it looks very much not normal, right? In the way it's defined, you're talking about dynamics, entanglements, and again, there's no temperature, there's not even energy here, right? Energy is not conserved. So, but yet it has all of those nice features of phase transitions that you would have in a 2D Ising model, right? Okay. So
can I ask another question? Sorry.
Yeah, please do.
So in the equilibrium critical points, I have various exponents, not only the nu and z. In these dynamical setups, do we have a similar exponent?
Yeah, so it's a good question. People have come up with new observables. So in particular, Michael Garland and David Hughes have come up with some observable that is kind of probing an exponent beta, like something that couples to another parameter. Hopefully it will become clear, like I will just mention a bit about the theory. So that theory, it has a whole spectrum that is so those things are not entirely a mystery now. So we don't know how to compute analytically all critical exponents.
Okay.
But we do understand why, there is an actual phase transition like in equilibrium behind it. And it has a whole spectrum of critical exponents.
I see.
It has an order parameter exponent and so on. It's just not, if you measure entanglement in this way, that's not the first thing you see.
I see.
Yeah.
So the exponents are not something exotic. It's connected to the equilibrium theory. So they satisfy the expected rules for the critical exponent.
Yeah, there's a well-defined stat. So actually what I'm going to show in the remaining time I have is you have an actual classical 2D StatMech model behind this.
Okay.
And so it
That's
has all
cool.
the properties you would think. Okay. And yeah. And so one thing I should say, there's one more exponent, like at criticality, this entanglement grows logarithmically. And the prefactor also gives you another universal quantity. Okay. All right. So again, in the last 10 minutes or 15 minutes I have, I'm just gonna I want to tell you a bit about the theory of this, just to give you one example. So far I was mostly about just mentioning examples, but not going really into the detail. All those examples sound very hard to deal with. And they all are in some way, if you think of the many-body localization transition and so on, those are all pretty hard problems that I wouldn't say are solved in any way. So let's think more about this measurement transition, right? So let's think about how can we analyze it from a theory point of view. So you want to compute entanglement as a function of, say, time, or at long times as a function of distance in this system. So it seems very hard because not only do you have to compute entanglement, which is usually hard anyway, and here on top of it, you're making measurements, right? And measurements in quantum mechanics, the way we learn about them, they're pretty unpleasant. So every time you make a measurement, you have to take a wave function, take overlap with it with state up and down. That will give you the probabilities to find the outcome. And after the measurement, you project, and then the wave function is not normalized, so you should renormalize it so that it's normalized, right? So and then and it's of course important to have a nice normalized wave function to compute entanglement. So in principle, it sounds extremely hard. So we want to compute entanglement entropies averaged over, again, I'm going to go back to my system of I have hard gates, random gates. That is actually going to make our theory a lot easier. Measurements that could be many locations, and I should also sum of the measurement outcomes. Okay. So it turns out it's actually doable, and so at least in a formal way. So again, what I'm going to think about is I have a circuit with gates and some measurements. And again, I'm going to think of quantum trajectories, which correspond to different outcomes. So it's going to be useful. So the thing I'm going to do is not normalize my wave functions after I make the measurements. So I could have many measurements, okay? And every time I make a measurement, I have a projector, so I'm going to lose some weights. And you can easily convince yourself that even if you have 100 measurements, and they can all have different outcomes. If you know about, you had measurement 1 that gives you spin up, measurement 2 that gives you spin down, and so on and so forth. And at the end of the day, you ask what was the probability that this occurred. This probability is just how much weight you lost. So it's actually just trace of rho. So it's not an entirely obvious result. So it is the first time I had to think about it to convince myself that this was correct. So you don't, it may be obvious to you, but basically you don't have to normalize the wave function every time you make the measurement. You can only normalize at the end, and this trace of rho actually, which is not 1 because you didn't normalize. So the norm of the wave function actually gives you the probability that you had to make measurements, that you made those measurements. Okay. Again, this may be obvious to you or may not be obvious to you. It actually wasn't obvious to me, and I had to sit down and convince myself with 3 qubits or something like this that this is indeed correct. Okay. So a bit more formally, what we want to compute is some quantity like this. Okay, so this is a bit more math here. So again, we have a circuit where each box is each green rectangle is a gate. Each blue circle is a position where you could have a measurement with probability p. And here I'm imagining I take a circuit. So you see I have a big average of a circuit where say, each circuit is given by a set of gates. And then I put in red the positions where I make measurements. Okay, so I had a probability P, and I ended up making a measurement. And for all of those measurements, I have different outcomes. And again, those outcomes are weighted by this probability, which is trace of Borrow, which is the so-called Born rule. So this is just putting the quantum mechanics of measurements, like, what is the probability to have, of course, in quantum mechanics, when you measure, the outcome depends on the state of the system, and this is taken into account here. Okay, so what we want to compute is, again, this entropy, entanglement entropy. I have to normalize the system at the end of the day, and I have to normalize the wave function or the density matrix at the end of the day. And I want to average this over all the measurement outcomes and over all circuits. Okay. So this is already like one step towards the theory, but it's still extremely hard to compute. So the thing I did here is to formalize a bit exactly what we want to compute. That's the entanglement entropy average over measurements. And so the non-trivial part is this trace of rho here. That's the weight of the measurement. Okay, that's the so-called Born rule of quantum mechanics. Okay, so how do we compute this? Well, so an approach that we've developed with my collaborators is to think of a replica trick. We have to compute the average of a log, and so usually in physics, when we see average of a log, I immediately want to use a replica trick. So you can use this formula, which is true with m is an integer. Okay, and assuming this is easier to compute, the average, then you can take m going to 0. Okay. So the same replica trick you have in disordered systems, in classical systems, and so on. And here it turns out that this is enough to allow you to formally compute this entanglement entropy. So averages of this type, okay, trace of rho a to some power, everything to some power, are actually something you can do. Okay, and they can be mapped onto a classical StatMech model. Okay, so this is the part where I'm going to skip the technical details. You can refer to the paper if you want, and I don't want to, bore you with things that are too technical. It's already technical enough as it is. Okay, but there are well-known formulas by now to average over many unitary gates, and there's there's some diagrams here. Okay, but so at the end of the day, if you do this and you do the math correctly, you end up with a statistical mechanics model, and except the degrees of freedom are a bit weird. And instead of being just Ising spins or something like this, there are actually permutations. Okay, so they live in some permutation group that act on those replicas. So here, okay, I should summarize a little bit. So N is the Renyi index. Okay, so that's the index of my Renyi entropy. M is that fictitious replica index that I introduce, and M should go to 0. And there's a +1 here, which actually comes from, this actually comes from this trace of rho weights. Okay. So this is a permutation of all those quantities here. Okay. So the claim, and again, it's not entirely, it's not obvious, you have to sit down and actually do it, is that this average of quantities of this type over all circuits can be mapped onto something that looks like a genuine classical StatMech model. Okay. So the details of the mapping won't be needed, okay, won't be useful. And so I'm just gonna, give you a qualitative picture on this that will explain a lot of what we see. So you have, again, a statistical model. You can think it's basically like an Ising model, except again, the degrees of freedom are like permutations that live in this Q, where Q is this, is related to those replica numbers. So what is entanglement entropy once you do this mapping? It ends up being the free energy cost of introducing a boundary domain walls. So the statistical mechanics model lives on this circuit, so it lives in 2D. And so once you do this 2D circuit, you want to measure, entanglement of, say, the boundary, say you waited some time and you want to measure the entanglement of that red region here. Okay, so effectively now, once you do the mapping, you have like a classical StatMech model, okay, 2D. And so now this entanglement is kind of acting at the boundary of that classical StatMech model. And so this gives you, like entanglement in that formal way, then that StatMech mapping is given by the following: is some kind of replica limit of some free energy difference. So, okay, if you forget about the replica part, which sounds complicated, it's actually good because we mapped it to something a lot more natural, right? Free energies are things we know well, okay? And so in just a 2D classical StatMech model. So the only hard part is like really the replica limits. Okay, and so you have two free energies. One, F naught, is just the statistical mechanics model, and FA is exactly the same StatMech model, except you have boundary magnetic field acting on that region. Okay, so that's why it's like creating a domain wall. So, okay, this is going to be we're done with the technical part. This is going to be the bottom line here. So we understand all of that.
Can I ask a question? Sorry.
Yeah, please go
so
ahead.
in the previous slide, so you said the entropy I'm looking at is the boundary domain or energies. Is it the bulk criticality or boundary criticality?
Yeah, so it's a good question. So actually, that's the slide I'm going to talk about. So it is going to probe both in some way. So there's going to be a transition which is driven by the bulk, but it's going to probe boundary criticality and boundary critical exponents. So the picture that we converged on, like in those papers, and there was a very similar paper by the Berkeley group at the same time as our second one, is the following, and I'm actually borrowing a figure from their paper because it looked nicer. So the picture is the following, that you have a StatMech model. Let's imagine, again, it's sizing, just to simplify things. Okay, and I claim the entanglement is like the free energy of introducing a domain wall. So let's imagine you have a ferromagnetic phase, right? So it's a StatMech model. It could be ordered. So you could have a ferromagnetic phase. Let's say it's an Ising model. And now imagine you have all your spins, the boundary are fixed to be up, but in that region where you compute entanglement, you fix it to be down. Okay, so that's what I mean. It introduces a domain wall in your StatMech model. And you ask how much free energy does it cost to create that domain wall? Well, okay, if you have a ferromagnet, that free energy cost is going to scale with the length of that interval. Okay, so that gives you volume law scaling. So now let's imagine you tune the parameter and like temperature in your StatMech model, which happens to be tuned by this probability P. And now you go to a paramagnetic phase, which is domain wall condensate. Now, actually, the free energy cost for this domain wall is just a constant. It doesn't scale with the size of the interval, okay, in the StatMech model. So this gives you a very nice picture where you can understand very qualitatively why you have a transition. So basically, in that language, the StatMech model has just a regular ordering transition. It starts in an ordered ferromagnetic phase that gives you volume law entanglement. And as you crank up P, you end up at you have a phase transition, and you end up in a symmetric paramagnetic phase, and that gives you entanglement scaling as area law. So this gives you an extremely nice picture, and it explains a lot of the scaling I already mentioned. Okay, so you started from this complicated problem of entanglement transition, and okay, admittedly we had to use like involved mappings and replicatrix and so on, but at the end of the day, what we have is a simple ordering transition in a classical StatMech model in 2D. So it doesn't get a lot simpler than this, okay? Except we have this replicatrix.
Can I ask another question? Is it because of the minimal area you draw? Is it the reason why the random tensor network figure you draw belong to the same universality as this one, or?
Yeah, so there's also, you can also, yeah, absolutely. So there's also exactly the same picture you can have for the random tensor network. So you can also derive a statistical mechanics model, and this statistical mechanics model is different, but it has the same symmetry.
I see.
So you could think it's essentially the same universality class. There's only one difference, which is this replica limit. It doesn't have this trace of rho factor, but otherwise it's really almost the same.
I see. Okay. That's pretty cool.
Yeah. So this is why, and you see why you have here some universality. In some way, like you actually have a genuine just equilibrium 2D classical phase transition behind this. Okay.
I see. That's pretty nice. I see.
So trace rho there reflects the measurements that you.
That's right.
I see. And what is the bone dimension of your quantum circuit? Is it also a tuning parameter, or?
Here it's fixed. I mean, it can be pretty much anything you want. Like you can just work with qubits. D = 2. All the numerics was done with qubits. In the StatMech model, we can take it to be whatever we want. And actually, it simplifies if you take that dimension to be large, and that's one of the last thing I'm going to mention.
Does it change the universality class, or is?
Only if you take D goes to infinity, but in general, no, it's the same universality class for any D. Yeah.
Thanks.
Yeah, so let me kind of wrap up because I guess I'm running out of time. So The nice thing is that naturally explains many scaling properties of that transition. We know a lot about, of course, ordering transitions, you know, and 2D models. So in particular at criticality, for example, okay, this is some CFT jargon if you like CFTs. But for example, we know how the free energy of a domain will scales. Okay, it scales logarithmically. Okay, and so it also explains why you have conformal invariance, because there's actually a classical StatMech model. Okay, and so it's described by a CFT. And the mutual information in that language is a 4-point function at the boundary of that model. Okay, so you were asking about boundary criticality. Actually, like this scaling dimension here is a boundary critical exponent. So there's some mix. You know, the transition is driven by the bulk, but there's some scaling properties which have to do with the boundary. Okay. So this is actually just my last slide that I want to mention. So far, of course, like I haven't used this. So I should say we have a very nice simple picture, but we don't know how to compute exponents. And the reason is the replica limit is very hard to take. Okay, so we get this very nice, you know, it explains a lot of the numerics, but it doesn't, we don't know how to actually get critical exponents for this. Replica trick is very hard. There's one limit in which it becomes extremely simple, which is if you take on-site Hilbert space to be infinite. So this is kind of like a large n limit if you want. So Youngmin, you were asking about D, right? So about the scaling, by the dimension of the on-site, you know, Hilbert space. So again, you could be qubits, but you could take that, you could take q dits and take D to infinity. Okay, so I take very large on-site spins. And there the partition function ends up being very simple. It's actually written down here. You notice I actually didn't write down my partition functions in general because they were horrible. But here in that limit is actually extremely simple, and it's just a well-known model of statistical mechanics, which is the Potts model. And the Potts model is nice. We know a lot about it. It has Q factorial states here, and we know how to take replica limits. So at the end of the day, we wanted to take m goes to 0 for my replica limit. Actually, that's this parameter Q going to 1. And it's, you know, again, well known how to analytically continue the Potts model for the number of states being a real number. And it gives you classical percolation. Okay. So this is kind of this picture here where you just, you know, you just put bonds, which is maybe, you know, kind of intuitive in that measurement transition. You can think it's almost like percolation, right? You put, you know, if your measurements percolates, you know, or not. So you could think maybe intuitively it's pretty natural. And at that limit, we can compute many things. We can compute the correlation length exponent, which is well known for percolation. It's actually extremely close to what people see in numerics. We can also compute the prefactor of this log, for example. Okay, so in that limit, everything is extremely well known and controlled. Unfortunately, when the on-site Hilbert space is not infinite, we believe it goes to a different universality class. And that was this kind of last slide I was drawing here. So this is, you know, there's an enlarged symmetry in that limit. And so we think in general, it flows to some different type of conformal field theory. Okay. So there's a lot of CFT stuff we did, and in particular, you can write down some field theories and Lagrangians and so on. Okay, so I'm not going to talk about this, but so the nice thing is you can really, you know, write down all the things we know about normal field theories. So here the complication again is that it's a, you know, it's a replica limit, and you have to deal with the fact that, you know, you have conformal field theories that have central charge 0, so they are very unpleasant, and so this is due to that replica limit. But otherwise, it's just a 2D conformal field theory or 2D statistical mechanics model. Okay, so I'll skip this last thing. So let me wrap up. Okay, I've talked about this new class of entanglement transitions. I think they are quite exciting in general, in the sense we didn't know about them. You know, they are very recent, right? So I think it kind of started with the many-body localization transition, and we're discovering new families. I mentioned 3 different problems that had entanglement transitions. I'm sure there are others, and there are others I haven't mentioned. You know, I mentioned this measurement transition can be mapped onto a classical StatMech model. So here it's pretty clear you have universality, you have everything we know. And a lot of the physics, again, doesn't depend, you know, this is of course a theory model, but like this transition exists even if you don't have all of those nice features of Haar gates and so on. In the future, so, you know, I'd love to get a better handle on field theory descriptions of such entanglement transitions. Of course, not all of those entanglement transitions are going to be nice and have a field theory behind them. When we're barely starting to really kind of classify those transitions, understand universality classes, critical exponents, and all those things. And so with this, let me thank you very, very much for your attention. Thanks.
Thank you. So the talk is open for the questions. Any questions, comments? Yeah, Pyeongmin. Yeah.
So, in principle, you can simulate the corresponding classical model and then measure the critical exponent there.
Yeah. So I mean, it's a good point. So the problem is the replica limits. So the statistical mechanics model we can write easily for when this replica index we had is an integer. So you see, like, just going back to the original formulation, it's naturally formulated as a sum of the permutations with some weights, right? So the problem is then you want to make Q equals, square root of 2 or something, which, and in order, so you want to basically give a meaning to that stat-mech model where Q is not an integer.
I see.
So this is not, like, there are other models for which we know how to do this. For example, for the POTS model, we know. For the ON model, we know. Okay, so the ON model, we know how to analytically continue. For example, the limit n going to 0 has a meaning. It describes self-avoiding walks and things like this. So the POTS model, even with one state, describes percolation. Okay, and the way this is done typically is by doing some kind of high temperature expansion. So you sum over the spins and then you get diagrams or things like this, and you can analytically continue there. The issue is we don't know what to do this for this model. It's complicated enough that we don't have that handle, unfortunately. So we can do numerics where, for Q equals 2, it's an Ising model, for example. So we don't know a lot, it's just the transition is just Ising universality class. And for Q equals 3, it's just, it has 6 states and whatever. And it's, and so the problem is we can do this for integer number of replicas, but we don't learn a lot about, we learn about qualitative features like this, which is true for Ising. But we cannot get the critical exponent this way, unfortunately.
I see.
So it would be a huge breakthrough if we could analytically continue this in any way and even do numerics. But yeah, so we don't have even a way to do numerics on this at the moment, at least.
I see.
Other questions, comments?
I have a comment.
Yep.
So basically, in numerics, we observe critical exponents that different with calculation picture that predict. For example, in our paper or in Nahu's paper, it has been found that the nu equals 2 for some cases. So what are you thinking about this?
So sorry, can you repeat? Like, are you saying the exponents are different in which cases? Sorry.
So for example, when you do finite size scaling for the steady state entanglement entropy, right? You can get the exponent nu.
Yeah.
So nu in the population picture is predicted to be 4/3, right?
Right.
And in some models, for example, the random Caliphate circuit, we found that this is close. But for example, in Nahu's paper, the original one, they have found in some cases, for example, in Hall circuit, the exponent is close to 2 more.
Right, I see. Yeah, so I should say I don't know what the critical exponent is for the correlation and the exponent. I don't think it's 4/3. So it's only 4/3 if you have infinite on-site Hilbert space. So of course, which is not, the regime you have, like most numerics is done. As far as I know, all the numerics have been done with qubits. And actually, so this was kind of a slide. So, this percolation fixed point, it's unstable to going to finite Hilbert space dimension. So basically, we know it's not percolation. It should not be percolation. My understanding was that many numerical papers found exponents close to percolation in some way. But you're right, like there are some cases where it was not the case. So I have no particular opinion on what the correlation length exponent has to be. I mean, it could pretty much be anything. You know, I mean, it could be 2. I have really literally no idea at this point. Unfortunately, we don't know how to compute it in any way. So it's only known numerically at this point. So the prediction, which is of course not testable in numerics, is that if you could really approach that limit of infinite on-site Hilbert space, you would get really classical percolation. But it is like the minute you introduce, you know, a finite Hilbert space dimension, it's like a relevant percolation, a relevant perturbation to that percolation fixed point, and you flow to something else, which has a different correlation length exponent, which at this point, unfortunately, we have, at least I have no idea how to compute.
Okay, thanks.
Okay, great. Is there any other question, comment?
So is the critical point, like, is the non-critical point known? Are there any known CFT that maps to this critical point?
Not really. I mean, it's a good question. Like, again, except the percolation limits, of course, which was like, yeah. So you know, that limit is of course classical percolation, which is a well-known critical point. No, it's a different beast. The thing is, they are like, you know, so okay, this is more on the like formal CFT thing that so like conformal field theories of this type. So they have like trivial partition function. So the reason you have a trivial partition function is because here you take a replica limit. So basically the partition function is 1 in the replica limit. So which is also true for percolation. So it's one of those problems where the partition function is trivial, it's just a number 1 or something, but the correlation functions are non-trivial. So the central charge of such theories is 0. So you can see this because the central charge is, you know, it controls the finite size corrections to the free energy. So if the free energy is a constant, it will have to be 0. And those CFTs are known to be, like, even in 2D, to be extremely bad. There's basically 2 examples we know well. Percolation is one of them. The other one is the ON model as n goes to 0. So those are 2, you know, limits we understand pretty well that have central charge 0. But there are many others. You know, typically similar CFTs occur basically, you know, in quantum Hall plateau transitions or things like this. Like when you do the replica trick and things like this, you get similar conformal field theories that have central charge 0, and, you know, it's a very long-standing problem. And they are, you know, so I would say it's basically in the family of conformal field theories we don't understand, and they're certainly not classified, and there's probably infinitely many of them. So yeah, but it doesn't map to any other like known problem that I know of. It just in that broad category of transitions where you use the replica trick and you get this kind of you know, non-unitary type conformal field theory.
It's not unitary. I see.
No, it's not unitary because of this central charge 0. Yeah, the only like nice unitary theory is trivial with central charge 0. Yeah, so it's non-unitary because of the replica trick. So yeah, it has many unpleasant features as a field theory. Again, I made it sound very nice because it's a 2D classical model, which is true. It's a lot simpler than the problem we started with. But unfortunately, as far as, you know, in the whole family and spectrum of 2D classical StatMech model, this is definitely in the most horrible possible. Yeah, so this is in the category that we don't know, we don't have a good handle on, basically. Okay, so we know a lot about just general scaling from conformal invariance, but yeah, we would need really we would need a way to analytically continue to the model to then be able to do numerics and maybe guess some structure about the underlying conformal field theory.
Okay, thanks. Yeah, thanks for the nice talk, by the way.
Yeah, thank you.
Other urgent question, comment before letting Roman to sleep? Is there any other question, comment? Otherwise, I would like to close the session. And let's thank the speaker again for the nice talk. And Roman, you are always welcome to visit Korea, or you can escape to Korea to
I would love to.
From COVID. Yeah.
Yeah, like whenever the COVID mess is behind us, I would really like that. Yeah, that'd be great.
Yeah. Okay, yeah, let me close this session. So yeah.
Thanks a
okay.
lot. Thanks,
Yeah.
everyone.
See ya.
Yeah. Bye.
Thanks.
Yeah, I will close the the meeting. Yeah. So I hope everything is going well with you in the Massachusetts, and the US. I
Yeah,
heard the
yeah.
things are horrible, but
I mean, everything is fine. Yeah. Cool. We're still. Yeah. No, everything is pretty good. Cool. Yeah. Thanks a lot for the invitation. I should probably get going now, but it'd be great to. Yeah, we should touch base informally one of these days. Yeah.
Okay. Yeah. Bye.
Thanks a lot. Bye.